Hi, this video is going to help with geometry, section 11.7, and it's the area of the volumes and similar solids. So it's more to do with the similar solids and how they are related. So let's look at Theorem 11.12 and go over what this theorem means. So first of all, this theorem says that if the scale factor, remember that's the relationship between the two similar figures, like is one twice as big as the other, that's our scale. Is one 1.2 smaller than the other, that's our scale factor. Of two similar solids is A to B, then the following are true. So if the scale factor is A to B, sometimes we write that as the fraction A over B, or the two dots, either way. And then these are the two things that we know. The ratio of their corresponding areas, oops, my R, it's kind of funny. Corresponding areas is A squared to B squared. So anything with area, that scale factor is squared bigger, because areas are square areas. They're like how many square pieces of whatever shape. If we had an inch by an inch, right, squares, maybe we would say there's 52 square inches in this shape. So area is all squares. So the scales are also squared bigger than each other. And then for volume, the volume, they're 3 times. So the ratio of their volumes is A to the third, B to the third. And let's see how we use that. So we know that the volumes are 3 times bigger, or 3 squared times bigger, cubed bigger, squared bigger. Okay, so let's look at some examples. So first of all, if I know that the volume of one shape is 729 centimeters squared, and the volume of another is 131 centimeters squared, cubed. These are volumed. Okay, find the scale factor. So if I know that these are my two volumes, then what is the scale factor? Well, we know it's third to third would be going down to our A squared, because these are volume, or would be going down to our A. So let's look at what we would think of this as. Think of it as we know A to the third over B to the third would equal 729 over 131. So to the third powers, now I want A and B. So to find A over B, you take the cubed root of 729 and the cubed root of 131. So because it's 3 times bigger, you got to figure out what times itself 3 times is a 729. Well, there's a key on the calculator usually for that. On the graphing TI-83 that I'm holding, it's in the math section here, and right at the front I go down to the third root here of 729 in your parenthesis, and I get 9, because 9 times 9 times 9 is 729. So this one's 9. Now the same idea, third root of 1331 happens to be 11. So the scale is 9 to 11. You could write this 9 to 11 this way, depending on how they want you to write it. We typically see it as a fraction, but either way. So that's our scale factor using the volume. So you might need to use a third root or a square root if it is a area. So I am going to, I don't want to write my next example out very much. or at all. I just didn't want to write it. So I'm going to show you my paper. Okay, so the lateral area of two similar cans are 1,019 and 425 centimeters squared. The volume of the similar cans, of the smaller can, is 1,157. What is the volume of the larger can? All right, so we know lateral areas, and then we know the volume of one. What's the volume of the other? So what we need to do is find that scale factor from the volume, or from the areas, to use to find that new volume. So what we first do is find that scale factor. Well, these ones are squared, so it's like a squared over b squared is going to equal 1,019 over 425. So if we want to find a over b, we take the square root. Okay, so the square root of 1,019 over the square root of 425 will give us that a over b. These ones don't work out pretty. They're totally a decimal. So what I'm going to do is I'm going to take the decimals and I'm going to divide them and then just get the scale factor that way. It won't really be a over b. It'll be just, well, a divided by b. So I'm going to do square root of 1,019, and I'm going to divide that by the square root of 425, and I put that in the calculator just like this. Square root of one divided by square root of the other, and that's about 1.548. So it isn't very pretty. So we're going to estimate this at 1.5484. That is our scale factor. So it's 1.5 bigger. Now that I know the scale factor, I can think about the volumes. So the volume of the smaller one is this, and we know that the larger one is this much bigger by scale factor. But when we're looking at volumes, it's 3 times, or to the third root, third power of our scale. So I have to take the scale that I got back down to that AB at 1.5484, and I have to take it to the third power. And that is going to be about 3.713-ish. And that is the number that is the scale for the volumes. So then I can take, because it's the smaller one that I know, and so I can times it by that scale and get, so times 1157, the volume of 495.48. So this is the volume of the large can. All right? So what do we do? No matter what we're given, area or volume, you go all the way down to the scale factor so that you can either square it or cube it, so that I know the relationship that you times by to get your other missing piece. And it works this way whether it was a volume or area. You just have to be careful of either taking the cubed root or the square root to get your scale. And then if it's area, you square. If it's volume, you third root the scale so that you can times it by. So that's kind of one of the problems you'll see. And the last problems that you'll probably see is, are these similar? So are these similar? Okay, let me draw that a little bigger on my other piece of paper here. Just because I drew them like teeny tiny on my notes. Oh, that's ugly. You'll get over it. And that should be dotted. That looks weird. All right, so. Man, this is why I use, oh, that should have been dotted. Rulers to draw things. Man, I'm not very good. So if all the way across the top is 18 on this one, and all the way across the top, the diameter is 12 on this one, and this one's 30, and this side's 20 meters, either way. If we know this information, are these similar? Well, these are actual side lengths, so we have to compare them. The way that we do that is we go, well, is 18 is the diameter to 12, So those are both diameter. Is that equal to 30 is to 20? So you're comparing those sides to make sure they have the same scale. And you could cross multiply to see that these are equal or reduce. Either way, I like cross multiplying. I think it's a little bit easier. So I'm going to go 12 times 30 and I get 360. And then 18 times 20 is 360. So yes, these are similar because the ratios were the same, or if you reduce the fractions, you'd get 3/2 on both sides, or cross multiplication is equal. So yes, they are. What would be the scale factor? If they're not, you don't have a scale factor. Well, I don't need to worry about volumes. I don't need to worry about areas on this one. The scale factor is 30 is to 20 or 18 to 12, either one that you want to look at. So 30 is to 20, that's our scale factor. Reduce that and you get 3/2. That's it. Okay, so those are the types of problems you're going to see in this section. Hopefully this helped.